All right, welcome to the Math 2413 Week 4 review. In this session, we'll mostly be going over some definitions of continuity. Again, we'll cover the intermediate value theorem. We'll also go over some limits at infinity, and also finally get into the definition of what a derivative is. Sound good? Perfect. Then start with just a little bit of review on what continuity is. We say a function f is continuous if one condition is true, but it really is like three conditions all rolled up into one. Continuous specifically at a point A. And that condition is the limit as x goes to A of our function has to equal our function value itself. Now you'll notice there are actually three things this implies. One, our limit exists. Two, and finally, three, that they're equal. So those are three conditions all really rolled up into one. A couple of nice things to remember are, you guys can see that, I don't care. First of all, polynomials, so anything like f of x, you guys know what polynomials are, but like x to the 7th plus 5x squared minus 1, anything of like this form where you just have x to integer powers, these are continuous everywhere in R, everywhere in the real numbers. So this is something that you should probably just remember. I don't think you will be expected to prove it at all. It's just good enough to know. Polynomials, continuous everywhere. Other functions are continuous on their domains. So those other functions include rational functions. What is that? One. That doesn't draw. There we go. Rational functions. Also logarithms and exponents. Trig functions. Root functions. And also inverse trig. All of these functions are continuous wherever they're defined, so continuous on their domains. And what I mean by continuous on domain, just in case any of you guys don't know, we can take a really simple rational function, 1 over x. Well, this has a domain of negative infinity to 0 combined with 0 to infinity, because we can't plug in 0. And we say that our function f is continuous from 0 to infinity, and it's also continuous from, well, negative infinity to 0, and then from 0 to infinity. So that's all I mean when I say continuous on their domain. And this is helpful because it lets us skip a lot of proofs of thinking, well, what would it make it continuous versus not continuous? If we know that all these functions are continuous on their domains, then it's a lot easier to just say, well, this function is continuous, rather than actually prove it out. So if we wanted to do just one quick example, let's say find where f is continuous. Well, we could really just, if our function is something complicated, like 1 over x squared minus 1, plus 3x to the 4th minus the natural log of 2x, well, we really want to address this component-wise. It's like three functions all put together. This one, and this one. Now we know that 3x to the 4th is continuous everywhere. So if you just put continuous on R. Natural log of 2x, if you remember, the natural log has a domain of everything larger than 0. And in this case, multiplying it by 2 isn't going to change anything. So our domain for the natural log is 0 to infinity, and the natural log is continuous everywhere on its domain. So natural log is continuous on 0 to infinity. Finally, we can look at our rational 1 over x squared plus minus 1. This is, we can't divide by 0, so in this case, it doesn't have -1 or +1 in its domain, so it's continuous everywhere else. Negative infinity, -1, union, -1, 1, union, 1 to infinity. And to figure out where our whole function is continuous, we just need to take where all three of these parts are continuous. So in this case, it would be the most restrictive bits. Clearly, we can't have negative infinity to -1 because this part isn't continuous on negative infinity to -1. And looking at just the intersection where they all overlap, you would get it's continuous on 0 to 1, union 1 to infinity. Make sense? All right. Let's go ahead and do a couple of practice problems just to make sure you guys get it. Same idea, just find where your function is continuous. And I'll give you guys a few minutes to work those out.
to like know the domains off the top of your head, and I don't.
Yeah. All right. Well, which one's tangent or arctangent?
I think I kind of guessed on tangent, but arctangent is not cotangent, so
It's
I'm
not
not sure.
cotangent. I'll give you a graph of arctangent really quick. So arctangent is like inverse tangent. So tangent normally is something like this, right? And then repeated a bunch.
Oh, I thought that one was cotangent.
This one is tangent.
Cotangent's the other way.
Cotangent is it's like the other way, with asymptotes in a little different spot. Arctangent is inverse tangent, so it's like reflected across the line y equals to x. Have you thought of inverses that way before?
So it's gonna be like that.
Yeah. So kind of like this. And we say it has a horizontal asymptote at negative pi over 2 and also at positive pi over 2. But what's its domain?
Oh, yeah. So then the domain of tangent is negative pi over 2 to pi over 2.
Well, that's actually the tricky thing.
I was like, did I get it right?
The domain of tangent, because tangent repeats like this, that is a terrible, that is not even tangent. So tangent repeats kind of like this, right?
Yeah.
It actually has vertical asymptotes spaced out every pi and starting at pi over 2. So it'll have vertical asymptote at pi over 2, 3 pi over 2, 5 pi over 2, also negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and so on.
So the domain would be
Right. Let's just see if everyone else is ready to go over it. How about that? Everyone ready to go over these problems? Perfect. So for this first one, fairly straightforward. Sine and cosine each have a domain of all real numbers. So when we multiply them together, we still get a domain of all real numbers. Negative 4x squared, it's a polynomial. It has a degree of all real, a domain of all real numbers. So it's continuous on all real numbers. The cube root of x, sometimes you might be tempted to think that the cube root of x only has a domain of positive numbers and 0. But because it's a cube root and not a square root, we actually can include negative numbers. So the domain of cube root of x is also all real numbers. So it's continuous on all real numbers. Then the square root of negative x, well, we can't take the square root of a negative number, so we can only plug in negative infinity to 0, because if we put a negative number in for x, well, the negative we have next to our x is going to flip that to a positive, makes it okay. And then we just take the most restrictive set, so that gives us negative infinity to 0 for where our function is continuous here. All right, for the second one, I am going to skip tangent for now and look at the other ones. Starting with arctangent. The graph of arctangent, for those of you who don't remember, looks something like this. It has a horizontal asymptote at negative pi over 2 and a horizontal asymptote at positive pi over 2. But its domain is all real numbers, so it is continuous on all real numbers. Next, we have log base 2 of x. All logarithms have a domain of 0 to infinity, but do not include 0. Now we finally have to look at tangent of pi x. So the graph of tangent looks something like this, but then it's repeated over and over. So we have a whole bunch of vertical asymptotes. All of these vertical asymptotes occur in our normal tangent graph, every pi. So starting with pi over 2, we have them occurring at intervals of pi. So the distance between two of them is pi. When we have tangent of pi x instead, we can think about almost shrinking it horizontally. So instead of having our asymptotes at pi over 2 every pi, well, suddenly we made the distance between them 1, starting at 1/2. So we'd have asymptotes at 1/2, 3/2, 5/2, etc. So then our domain, our domain would be all real numbers except 1/2, 3/2, 5/2, 7/2, and so on, as well as the negative ones. So -1/2, -3/2. You could represent that as all real numbers without let's see. We could represent this using what's called set builder notation. And it's basically like saying, I want numbers of this form provided that k is an integer. And I know this looks really complicated, so usually in your classes, what you'll probably be writing is something like this. All real numbers except, and then you might put like 1/2, 3/2, 5/2, ... and maybe you could put dots the other direction too, because this is also clear what you mean. So then that's where our tangent function has its domain, because it's a trig function, it's continuous on that. So then for our whole function, we simply take the most restrictive parts. In this case, all real numbers is less restrictive than 0 to infinity. So we take 0 to infinity. We also need to include this restriction, except all the numbers 1/2, 3/2, 5/2, etc. Although in this case, because we've already taken 0 out, we can just start with 1/2. Does that make sense?
For number 1, would 0 be open or closed?
Oh, you are correct. For number 1, 0 would be closed. That is my bad. Can I re-explain how we get the overall domain? Certainly. So we take the overall domain from the most restrictive parts of our individual functions. So let's say I wanted to do let's say I just wanted to take a really weird and kind of dumb function. F of x is equal to the square root of x plus the square root of negative x. Well, the square root of x has a domain 0 to infinity inclusive, and then the square root of negative x has a domain of negative infinity to 0 inclusive. Now, I want to take the most restrictive parts, so only where all of these overlap. And if we wanted to sketch this out on a number line, we would have everything from negative infinity to 0, and everything from 0 up to positive infinity. The only spot they overlap is the point 0. So our domain would just be the single point 0. And this makes sense because if I try to evaluate my function at any point other than 0, let's say f of -1, well then I'd have to be taking the square root of -1 plus the square root of that -1 can't be in our domain because we can't evaluate it. And the only way we can get the total domain is by making sure we can evaluate our function at every single point within it. That means taking the most restrictive parts, only where everything overlaps, where you can define everything. Does that make sense? Yeah, no problem. All right, are we good on continuity of functions like this? All right, then let's move on to the intermediate value theorem. And the intermediate value theorem is quite useful and Not too difficult. So the intuition behind the intermediate value theorem is basically, if you're trying to get from one spot to another spot and your function is continuous, you have to pass through every spot between them. So one thing I could say is, like, if I had a function, or I guess 2 points here and here, and I wanted to draw a continuous line between them, well then for any y value I can put between them, the line I draw is going to have to cross this line. Because if it doesn't, well then suddenly somewhere I'm going to have to pick up my pen to finish drawing it. So that's kind of the intuition. What can also happen is instead of crossing just once, I can cross as many times as I like. The intermediate value theorem just tells us we have to cross at least once on that interval. So if we want to define this more formally, we say, first off, we need to list our conditions. If our function f is continuous on a closed interval from 0 to, or from a to b, not 0 to 1, and we also know that our starting value is not equal to our ending value. Basically, we have a y value between our start and end. Well, then we know that for any y value, we're going to call it n between the points so for any y value between our start y value and our end y value, there has to be a point such that our function evaluated at that point is equal to our intermediate y value. So not too difficult. Any questions about the definition? Go for it.
Why does it have to be a closed interval?
Why does it have to be a closed interval? Well, it's usually because, what if we had a whole situation like this, where our function is continuous on an open interval, right? But what if I define my function to be somewhere up here at that point? Well, then I don't actually have to cross this line, because it's still continuous on this open interval. But there is no point where my function actually crosses this line on my open interval. So that's really the intuition behind why it's an open interval. Good question, though. What is the difference between n and c? N is your y value. C is your x value. So I'm going to replace this with just a single crossing point. This horizontal line is like y equals to n. C would specifically be the x value at which this happens. So you can see that your function evaluated at the x value c should give you your y value of n. Make sense? Perfect, perfect. All right. So let's go ahead and do an example showing maybe why this is useful. Show that f of x equals x cubed minus 7x squared plus x plus 2 has a root between 0 and 1. So if you'll recall, a root is where your function is equal to 0. So in order to show this has a root, I'm going to try and show that f of 0 or f of 1, f of 0 and f of 1 have different sign values. In other words, one is above 0, one is below 0, then by my intermediate value theorem, somewhere my function is going to have to cross 0 between 0 and 1. First off, I need to make sure f is continuous. It's a polynomial, so obviously it is. Then I find out what f of 0 is. It's pretty easy. All of my x terms go to 0, so I'm left with just positive 2. Next, f of 1, I get 1 cubed is 1, minus 7 times 1 squared is minus 7, plus 1 plus 2. That gives me negative 3. Well then, oh, that's not, there we go. Since f of 1 is smaller than 0, and f of 0 is larger than 0, and because f is continuous, well then, by the intermediate value theorem, it's often abbreviated IVT, there has to be a 0 so there exists an x value c such that f of c is equal to 0. So then we can say f has a root between 0 and 1. Make sense? Yep, fairly straightforward. All right, let's do a couple of quick practice problems. That's just x. Next. All right, good luck. I'll give you a couple minutes to work out those, and we'll move on.
short version of what you wrote. And this one is too basic, but just negative 10.
Yep.
Because it's such a real root, and I'm like, okay, I don't know what that means, but I know root is a zero, so I just.
But you don't necessarily need to find, you just to show that it has one, right?
Yeah, that's a polynomial, so it should have one.
Okay. How did you show it has
Especially this domain.
one? Not necessarily. How do you show that this one?
Because of plugins.
Okay. So this problem, the difference is you don't have a range, right? So maybe you could decide on one and see if it works. Because if it gives you a number bigger than zero, smaller than zero, somewhere between in your range, you have to have one, right? That makes sense.
Yeah.
Yeah. All right, are we ready to go over the problems? I didn't get very much time. Okay, let's go over problem 1. So this is pretty much the same as the example problem. We need to plug in f1. First of all, it is a polynomial, so it is continuous. F of 1 is, of course, equal to 1 to the 4th plus 1 minus 3 gives negative 1, from 1 plus 1 minus 2. Secondly, we take f of 2, and we see 2 to the 4th plus 2 minus 3 is 2 to the power 4, which gives us 15. Now we can clearly see that negative 1 is smaller than 0 and is smaller than 15. So then f of 1 should be smaller than some value f of c, which should then be smaller than f of 2. And we can say then, at some point, because f is continuous, f of c has to equal 0. So f has a real root from between 1 and 2. Now the second practice problem is a bit trickier because there is no range attached. But the principle is the same. We just need to find one value smaller than 0, one value greater than 0, and say, well, one smaller than 0, one is greater than 0. At some point, because our function is continuous, we'll have to cross 0. So I like picking easy things. I actually did go with negative 10 and 10 because I could see that that would give me a pretty clear difference. So if I take f of negative 10, that would get me negative 10 cubed minus 7 times negative 10 minus 1 gives me, this is negative 1,000 plus 70 is negative 930 minus 1, negative 931-ish, I think. If I'm a little bit off, I know I at least got my sign right on this, and that's so much bigger that it doesn't really matter what exactly this is. I just know it's very negative. F of positive 10 would be positive 10 cubed minus 7 times 10 minus 1, which I believe gives 929. And again, I just know that this is very positive, so even if I'm a little bit off, I still know that I have something negative here and something positive here. So then there should be a c value between negative 10 and positive 10, so that f of negative 10 is smaller than f of c is less than positive 10. So then at some point, by my intermediate value theorem, I can say that f of c equals 0 for some value c, specifically on the interval from negative 10 to positive 10. Now I could probably find more restrictive intervals. Negative 10 to positive 10 is definitely not the only one that would work here. But it is the one that I thought of first, so that's what I went with. Make sense to everyone? Cool. All right, let's move on to some limits at infinity. If they gave you an equation with only positive outputs, would you say there are no roots? Yes. So one quick example is if you just took a quadratic that doesn't intersect the x-axis at all. This is an equation with no real roots. So there are no x values where you plug in x, you'll get 0. But you can't really use the intermediate value theorem to prove that. You would have to use some other method. Good?
I have a question. So the IVT could only prove things are right, not the wrong?
Right. The intermediate value theorem can only prove that there is a value between two other values. It can't say, well, there are no values below this point. That's something you'd have to do probably with, you could do it with calculus pretty easily, but you guys haven't hit that point in the course yet, so we won't cover it now. All right, next topic. We're shifting to limits at infinity. And you guys have probably seen these before. It's like finding horizontal asymptotes. So we say that a function has a horizontal asymptote we'll call it h, if either the limit as x goes to positive infinity of f of x is equal to h, or the limit as x goes to negative infinity. That is kind of atrocious. As x goes to negative infinity of our function is equal to h. So either of these can work, and either of these will give you a horizontal asymptote. One good example is, of course, your arctangent function. Because everyone forgets about it, I'm going to use it as an example a lot. We have one horizontal asymptote as x approaches negative infinity. That is negative pi over 2. We have one horizontal asymptote as x approaches positive infinity, and that is positive pi over 2. You'll notice it's not necessarily the same on both sides, but they are both horizontal asymptotes. All right, so now let's actually look at how to solve limits at infinity. So I think what you'll most frequently see in this course is questions asking for the limit as x goes to infinity of some kind of rational function. So for example, x squared plus 1 over 4x. And when you have functions like these, rational functions, you really want to ask yourself, is this top-heavy, bottom-heavy, or balanced? And what I mean by that is we look only at the largest term in the numerator and the largest term in the denominator. So looking at the numerator, we have an x squared and we have a 1. The largest one is the one with the higher power, in this case x squared. And looking at the denominator, well, 4x is the only thing there. You do want to keep your coefficients attached. Then you need to ask yourself, well, which is higher power? X squared is obviously a higher power. It's got a power of 2 as opposed to just 1. So because the top has a higher power than the bottom, we call this, or at least depending on who your professor is, some people might call this top heavy. And what this means is that the numerator is growing faster than the denominator. Or in other words, when your numerator is growing faster, it means your number is getting larger. So if you get larger and larger as x goes to infinity, you will, of course, be approaching infinity. There are 3 cases for what can happen with rational functions. It can be top-heavy. And as we've seen here, top-heavy, the limit goes to either positive infinity or negative infinity, depending on the sign. So for example, if instead of this we had negative all this, then we would approach negative infinity instead. but that's just checking the sign. If it's top heavy, you know it has to go to positive infinity or negative infinity, and then you just consider the sign. Erase my highlighting there. There we go. Another case is we can be bottom heavy. And this is where the degree of the bottom is greater than the degree of top. I'm going to abbreviate it like this. Well, when we have a function that's bottom heavy, for example, I'm just going to take this previous one we had and flip it upside down, 4x over x squared plus 1. Well, then our denominator is increasing faster than the numerator, so we're dividing something into smaller and smaller chunks. So we're getting less and less over time, so we will be approaching 0. And that is true for all bottom-heavy functions. We don't need to worry about sign because positive 0 is the same as negative 0. The last situation we can have is what's called balanced. And this is when the degree of the top is the same as the degree of the bottom. Well, in this case, I'm just going to take x plus 1 over 4x. If we look at the largest term on the top and the largest term on the bottom, this is where you actually do need to pay careful attention to your coefficients. For a balanced function, all you do is you take the coefficient on top, so 1, and divide it by the coefficient on the bottom, 4. 1 over 4 is your answer. And the reason behind this is that as x goes to infinity, basically all of your smaller terms, like this one here, well, they become so insignificant. You can think about it like, well, when x is 1, the plus 1 is going to mean a lot. When x is 100, it's going to mean considerably less. When x is like 1,000,000, you're barely even going to notice the plus 1. So it's basically going to be like 1,000,000 plus 1 over 4 times 1,000,000, which is almost the same as 1/4. You'll just be getting closer and closer to that point where you just have this exact fraction, because your smaller terms are basically going to vanish. So these are the 3 situations you can have when you have limits at infinity with rational functions. So let's go ahead and do some practice problems. Sound good? Perfect. And yes, I know I'm throwing a kind of one that's a bit different at you at first. So feel free to try some of the other ones before you try that one, if you're uncomfortable with it.
Is that a 9?
It is a 9 on top. Make that a bit more clear. I should probably write larger. I will give you guys a few minutes to work through those.
I mean, I reasoned through it, but I also am learning this for the first time right now. They did.
Oh, they did.
I didn't.
Oh, I see.
I didn't think so.
Can you explain your reasoning?
Well, if X is going that way, I was thinking because this is top heavy, this is still looks like that. So even if it's going that way, it's still going up.
Right. So right about it going to uninfinity. Let's think about it like a negative in top. Negative times a negative is just like X squared. It gives you a they're divided by a
Positive?
well, X is negative, right? Since it's going to negative.
Oh.
So you have positive divided by negative, which should give us a
Negative. Okay.
yeah. It's not too bad.
So even when it's top heavy, you still have to consider the bottom.
You still have to consider the bottom in case it affects your sign.
Oh, okay.
For this one, is there a log that we can use to use the up front?
This is just 3 ln x.
Right. And did you notice that other note I wrote over there?
This was go faster than any bottom.
What about the one below it?
Blocks was slower.
Yes, answers.
For like evil, it's 0, right?
Right.
Okay, so then I think they're right. Maybe.
For this one, it's what you use.
Well, as element goes to infinity, just get bigger and bigger, so anything divided by the weak number of 0.
Right, but X also goes to infinity, right? Right.
Yeah, I might have taken a shortcut on that. Yeah.
Yeah. I wrote a couple of notes up there. One of them is long to go slower than any polynomial. So should that one be top heavy, bottom heavy, or balanced?
Well, my teacher told us not to do that. We have to do like the long way where you factor out things. So it gets me the right answer more often. So it's at least that.
Yeah.
But because it is a long way, I kind of skipped it on this because I thought I could get away with it. But
Yeah, I mean, should you have backward natural numbers and exponents in there? I guess you could, but let's try going over some of these. All right, let's get started. I'm going to start with part B because this one is probably the most straightforward, and I also probably should show the other method of that's a bit more formal than just looking at top heavy, bottom heavy, or balanced. Thank you. I'm going to show that now. One method you will often see done is to identify the largest power. So in this case, you have an x squared on top, x squared on bottom. Your largest power is x squared. So one method to solve these, if you don't really care to think about top heavy, bottom heavy, or balanced, is you can divide everything by that greatest power. Well, when you simplify this, now you can evaluate your limit. It's really easy to see that 1 over x squared and 3 over x squared will both go to 0. So then you're left with 8 plus 0 over 7 plus 0, or just 8 over 7. Now, some of you guys might have professors that would like you to divide everything by x squared and show a more formal method. If you do, good luck. I personally prefer just looking at top heavy, bottom heavy, or balanced. And I think I probably had a different professor than you guys then. But this is an alternate method of solving these. All right, so that is B. For these other ones, we can take. Do you have a question?
You said divide by the largest exponent in the problem?
Right. Divide by the largest one. If we divided by something smaller, it wouldn't necessarily help us because then terms wouldn't just go to 0 or constants. Yeah. All right. Let's take a look at part A. I wrote this note out here a little bit after writing down all the problems. Exponents go faster than any polynomial. This means that an exponential will outweigh any polynomial, so this is bottom heavy. Because it's bottom heavy, it'll go to 0. All right, we already said part B was 8/7. Part C, we can see that an x squared term is larger than just an x term. It's top heavy. You can divide out everything by x squared if you feel like it. For time reasons, I'm probably not going to. This one, we know it has to go to either positive infinity or negative infinity. For problem B, did we take the greatest degree on the bottom? We actually just took the greatest degree in the problem. It just so happened that because it was balanced, it was also the greatest degree on the bottom. It could be that your professor wants you to do it for the greatest degree on the bottom. Like I said, I'm actually not that familiar with this method. Like I can see why it works. E to the x is not necessarily the largest possible power with limits at infinity. There are a lot of functions that are really weird, but I think it's probably the largest possible power that you will see with limits at infinity. Although I guess one thing to note is exponentials also have like their order. So like we can say that x is smaller than x squared. Well, we can say that 2 to the x is smaller than 3 to the x. And we know that e is actually between 2 and 3. So e to the x is actually smaller than like a 3 to the x. So that's just one thing to make sure you're aware of. Exponents are larger than polynomials. They're not necessarily larger than other exponents. And to answer your question, I think you probably should be taking the greatest degree on the bottom after thinking about this for a second. So yes, I would go with greatest degree on the bottom to answer your question. All right. Perfect. Now then, problem 4. Part C. I actually will show you what might happen if you did try to divide by the greatest degree. Because I think it's interesting. So let's say we did try to divide by the greatest degree. We would then say it's the limit as x goes to negative infinity of x squared over x squared plus 1 over x squared. It's the limit as x goes to negative infinity of 1 plus 1 over x squared over 4 over x. Well, then when we plug in negative infinity, this denominator is actually going to go to 0. And that gives us both 1 plus 0. And that's not necessarily solvable because you can't divide by 0. So that's my reasoning for why you should just divide by the greatest term on the denominator. So that would be dividing everything by an x instead of an x squared. And when you solve it this way, we would get that's x plus 1 over x all over 4. Solving our limit, we would get something plus 0 over 4. In this case, because x is going to negative infinity, we need to make sure we're keeping our sign. So that gives us negative infinity. Make sense? Cool. All right. For part D, similarly to how exponents are faster than a polynomial, logarithms are slower than in a polynomial. In this case, even though we have an x cubed in our natural log, we can really think of the natural log of x cubed using our power rule for exponents, or for logarithms, sorry. That's the same as 3 natural log of x. So exponents inside of our logarithms don't really do anything. And because natural log of x grows slower than x minus than just x, which is polynomial, this is top heavy, it goes to infinity. Part E. Well, we know that trig functions are bounded between -1 and 1. So this is actually a great instance of when you could use squeeze theorem. If you remember from last week, we went over squeeze theorem. We can say that -1 is smaller than sine is less than +1. That should be a +1. So then the limit as x goes to infinity, I should just zoom in. There we go. Of -1 over x would have to be less than or equal to the limit as x goes to infinity of sine of x over x is less than or equal to the limit as x goes to infinity of, again, 1 over x. And these two outside limits are really easy. They're both 0, so our middle term has to be 0. Another way you could think about it is trig functions, or at least sine and cosine, not necessarily tangent, grow slower than polynomials. This is not true for tangent, so just apply that for sine and cosine. But squeeze theorem is a better way to show it because it's more formal. All right, and finally part F. We need to consider, again, the largest term on top and the largest term on bottom. In this case, on top, our largest term is 3x squared as well as the square root around it. So a lot of the time, students will forget to include the square root portion, but it is important. And our largest term on the bottom is 4x. So our largest term on top is square root 3x squared. So if I simplify that, that is square root of 3 times x. And you'll notice on the denominator, I have 4 times x. So this is actually balanced because I have degree 1 on the top and on the bottom. If you were to use your more formal method of dividing by the largest term on the bottom, you divide everything by x. It would, of course, become an x squared inside your square root. So we look simply at the coefficients, the square root of 3 and 4, and that is our answer. For E, could you also say that the x inside does not count as the highest power inside the parentheses? I mean, I don't really want to say yes because sine of x is really something quite different from x. So I could have, for part E, taken this whole entire portion and said, I want sine of e to the x squared. Well, really, e to the x squared, even though it's really a lot bigger than x, when I take the sine of it, it's still going to have to be between -1 and 1, because the sine of anything has to be between -1 and 1. So we can't really use what's inside the parentheses as a good judge of what's the largest power. It all comes down to the sign itself. Does that make sense? Yeah. Could I do problem F with negative infinity? Sure. So negative infinity, it will change things a bit, for sure. Come on, OneNote. All right, going to give OneNote a minute to glitch out. There we go. Okay, problem F with negative infinity. I'm going to do it down here since running out of space. Limit as x goes to negative infinity this time of the square root of 3x squared plus 1 all over 4x. So the way I like to approach my negative infinity versus positive infinity problems is first decide where it's going to go, positive infinity or negative infinity, and then consider the signs. In this case, we decided it's going to go, because it's balanced, to something like square root 3 over 4. Now, how my positive infinity and negative infinity affects that is it might change the sign. So we really just approach it by looking at what's the sign on top and what's the sign on bottom. On top, I have negative times a negative squared, or sorry, a negative times a negative since we have x squared. Negative times a negative gives us a positive. We take the square root of a positive, it's still a positive. So on the denominator, we have 4 times a negative gives us a negative. A positive over a negative is a negative. So our end result should be a negative. If you want it more formally, we can, of course, divide everything by x. In this case, we would get square root of 3x squared over x squared plus 1 over x squared all over 4x over x. This would get you the, well, see, this would actually end up giving you a different answer. Let's see, I don't really know exactly how to get around that off the top of my head.
I think I did it a little different.
You think you did a little bit?
You want to see mine?
Yeah, let's take a look.
So instead of dividing, if you control this to factor out, so you factor out absolute value of x squared, and then x on the bottom, and then so because it's negative, this would become negative x,
Right.
and then this would cancel out, and this would be negative 1 on the top,
Okay.
and then it's negative square root 0.
Cool. All right. One of our students here has helpfully decided to save me. So instead of dividing everything by x, we're going to factor out an x squared on top. So when we factor out an x squared, it will become the absolute value of x squared times 3 plus 1 over x squared all over 4x. Since we are approaching a negative infinity, we would essentially have a negative on that sign. So after canceling things out, that would give us negative absolute value of x as we approach the positive infinity of square root 3 plus 1 over x squared all over 4. Plug in infinity. That, of course, gets us negative. Oh, what am I doing? That should be just a regular x, sorry. And that would give us negative square root 3 over 4. Yes, sorry, when I factored out my x squared, I forgot to take the square root of it, so there you have it. Did that answer your question? All right. Now, all right, we are starting to run out of time, so I'll just briefly go over. Did you guys start derivatives this week or this last week? All right. We can really quickly cover the intuition behind it, and because it's cool and I like it. So when you hear the word derivative, really what you should think is slope. What's the slope of my function? Because your whole derivative is actually based off of your slope formula. So if you have a function like this, and you have 2 points, well, it's really easy to find the slope between them. You have your regular slope formula. If this is x2, x1, or x2, y2, there we go. And this point is x1, y1. Well, then your slope is y2 minus y1 over x2 minus x1. Well, the whole idea of a derivative is we want to be able to take the slope at a single point. So instead of having these 2 separate points, what we're going to do is we're going to take one point and we're going to take a distance away from it, h, like that. Well, if this first point is x comma y, well, we can take our slope as being f of x plus h, because that would be the y value at the second point, minus just f of x, which is our y value at our first point, divided by x plus h, our x value at our second point, minus x. And you'll notice our x's cancel on the bottom. We get f of x plus h minus f of x all over just h. Now, the derivative is what happens when we let this distance h between our 2 points get closer and closer to 0. So our formal definition of a derivative is the limit as h approaches, not infinity, 0, as h approaches 0, f of x plus h minus f of x all over h. And there are a few different definitions of a derivative. They all basically share the same idea. You might see them written slightly differently, though. So this is the whole intuition behind it. I'll go ahead and show a quick practice or a quick example problem. Let's say I wanted to find the derivative of f of x is equal to 4x squared plus 1. So find the derivative. You'll also see it written as like slope of tangent line. Because the slope of the tangent line is the same as the derivative. So in order to find the derivative, all I do is I plug my function into my definition. So the limit as h approaches 0 of f of x plus h minus f of x all over h is the same as the limit as h approaches 0 of 4 times x plus h squared plus 1. This is f of x plus h minus 4x squared plus 1. That's just f of x all over h still. Now, if I multiply everything out, that becomes the limit as h approaches 0 of 4x squared plus 8xh plus 4h squared plus 1 minus 4x squared minus 1 all over h. Now I can cancel a few things. I have a 4x squared minus a 4x squared, a positive 1 minus a 1. Now I can actually solve my limit by simplifying algebraically. I'll write it right here again just to make it clear. Everything on top has an h, so I'm going to factor an h out. Now I can cancel an h on top and bottom. And finally, I can plug in h is equal to 0, and that gives me just 8x as my answer. So the derivative of 4x squared plus 1 is just 8x. That whole process makes sense? All right, so then the cool thing about this is, if we drew out the graph of 4x squared plus 1, it'll be kind of like a spiky parabola. I'm going to draw it nice and wide, though. Well, then at any point we pick, I can tell you the slope of this tangent line right here. It's just going to be 8x, whatever this x value is. The slope, 8 times that x value. Here, if this is negative 2, slope, negative 16. Easy enough. All right. Well, are there any questions? Ooh. In that case, I will go ahead and